Hello. In today's video, I would like to say a few words about the continuity of a function and its relation with sequence of real numbers. As we all know that a sequence of real number xn is said to be convergent to a real number L whenever we have mod of xn minus L less than epsilon for all n beyond a threshold limit. That means this sequence of real numbers becomes very close to this limiting value after a fairly large number capital M, and whenever these members of the sequence we pick up, they became arbitrarily close to this L. And in a different notation, we may as well write that a sequence xn is said to be convergent to a real number L whenever we have a specific epsilon neighborhood of L, which may be represented as the open interval L minus epsilon L plus epsilon centered on L. This is an epsilon neighborhood of L, or a open interval centered on L. Whenever we have such a small epsilon neighborhood centered on L, we have these xn sequence member of this sequence belonging to within this interval for all m which is larger than a prefixed large number, say m1. Okay, so all these we may write here this type of notations also for all mi which are greater than a prefixed large value capital M. So there is a fixed large value capital M, and all the members of this sequence for mi's which are larger than this capital M, that means this may be x capital M1 or x capital M2 or x capital M3, then all M1, M2, M3 must be greater than capital M. Then they will be arbitrarily close to L or belong to the epsilon neighborhood of small l. Now, this concept may easily be extended to include the continuity property of a real valued function. Let us illustrate or remember, or rather recapitulate the basic idea of a continuous function, starting from the definition of limit. Whenever we say that a real valued function fx has a limit capital L as x tends to small a, we mean that for all mod x minus a less than delta, we must have mod fx minus capital L less than epsilon. So that is the basic definition of limit of a function, and this may be written in a different notation, that whenever x belongs to delta neighborhood of A, we must have fx within the epsilon neighborhood of capital. And obviously these delta and epsilon are both arbitrarily small positive number. As far as the concept of limit is concerned, we don't have to say any word about the relation between delta and epsilon. But whenever we extend this concept of limit to the concept of continuity of a function, we should be a bit rigorous or precise. Continuity of fx defined at x equal to a is such that we must have limit of fx as x tends to a becomes equal to fa only. So the functional value at this point is equal to the limiting value, and that is the basic concept of continuity of a real valued function at a point. Okay, so this is very vital. A function fx, real valued function, is continuous at a point whenever the limiting value of fx as x tends to a, that point at which we are considering the continuity of fx, is equal to the functional value. And whenever we can extend this definition throughout an interval, we have a function which is defined on a domain of definition AB. This may be a open interval or a closed interval. The domain of definition, we better write it as capital A, a set of real numbers, and this maps, this is the function maps this domain of definition to real number. That is why it is called a function of real numbers or a real valued function. So this function is continuous, is said to be continuous in an open interval, say I. Or say AB. Whenever for all xi within this AB, we have limit of fx as x tends to xi is equal to f epsilon. So that is precisely the extension of a continuity of a function at a point and throughout the interval. Whenever throughout the interval we choose this xi, in any part of this interval, we have deliberately chosen the interval as a closed and bounded interval. It may be an open interval, but any point within this interval, if we take any point xi, then this is a true limit of fx as x tends to xi is equal to the functional value of f at xi. Now, this basic concept of limit and continuity may be extended or may be juxtaposed with the concept of sequence of real numbers. How? Let us study it. Just now we have learned about the concept of the limit of a sequence. Now we just extend the concept of sequence of real numbers the definition of continuity of a real number. And this is termed as sequential criteria. Now, what does it actually mean? The sequential criteria or sequential definition for the continuity of a function fx is defined as if fx is continuous at a point x equal to a, then we have for any sequence xn, any sequence of values xn converging to this particular value a corresponding sequence of real numbers fxn which will converge to fa, and that is the sequential criteria, and this is the sequential criteria of continuity of a real valued function. So I repeat that a real valued function fx is continuous at a point x equal to a means the sequential criteria is stated as we have any sequence, if we have any sequence xn of real numbers which converges to a, we must have a corresponding fxn. Since this fx is defined, so respective to each sequence of values xn, we have another sequence of values fxn, and whenever this xn converges to a, we must have fxn converging to fa. Obviously, that is a sequential criteria of this function fx to be continuous at a point. So this is the sequential criteria of continuity of fx at a point, and whenever we want to extend it to interval, we just wipe out this point and put the term interval here, and we say that whenever fx is continuous in an interval I, then we have for any sequence xn converging to a particular point, let's say x star, where x star is in I. X star may lie anywhere in this interval, and for all those sequences xn which converges to any of x star within this interval, we must have a corresponding fxn, a sequence corresponding to this sequence, and that will converge to the value fx star only, and that is called the sequential criteria of continuity of a real valued function in an interval. Earlier we have defined the continuity at a point. So that is the extension of the definition of continuity in an interval from the definition of continuity at a point. So these are very crucial and subtle points one should learn step by step to relate to the concept of sequence of real numbers, which helps us to unravel the different properties of a real line, or we may say that the properties of real number. We all know that the real line is extended from plus infinity to minus infinity, centering on the special value 0. This is termed as origin. Now we would like to say one or two words about the properties of this real line. We all know that the real line is ordered. We have Peano's axiom. We all know that real line is dense. What does it mean? It means that whenever we have any two real numbers x and y, and since it is ordered, either x will be less than y or x will be greater than y or x will be equal to y. There is no other option, and whenever we have x less than y, we must have another rational number or irrational number which lies between x and y. Whatever be the values of x and y, we can squeeze another real number in between them, rational or irrational, and that is the denseness property. And we have the ordered property which is given by Peano's axiom, which states that whenever we have a real number x and y, we must have x less than n into y, where n is a natural number. And all these properties may be unraveled with the help of sequence of real numbers. I would like to mention just three things of this sequence of real numbers here. A sequence of real number may be convergent and may be divergent. Whenever a sequence of real number is convergent, then we may say that this sequence is bounded. But the reverse is not always true. That means a bounded sequence may not be convergent. Okay? We have earlier said what we meant by the convergence of a sequence. Xn converges to a particular value L whenever mod of xn minus L is less than epsilon for all n larger than a prefixed large number. So after a particular threshold value, all the xn's club or clutch near L. L becomes the limit point or attractor of all the members of xn. And whenever it is divergent, we don't find a particular limit and the sequence becomes unbounded. Obviously, when a sequence diverges, it becomes unbounded. So boundedness is a property which is closely related with the convergence of a sequence of real number. Okay? And we all know that real line or the real numbers has the property of completeness. That is another very important property of a real number. Completeness property. What does it mean? It means that whenever a set of real number A is bounded, whenever a set of real number A is bounded, we have a least upper bound or a greatest lower bound. When A is bounded, A has a upper bound or A has a lower bound. That means all the members of A is less than a particular value, strictly less than, then it has a upper bound. And if we have all the members of A may means members of the set A, are greater than a very fixed small m, then we say that this set A has a lower bound, is bounded below, bounded from below, and it is bounded from upper side. You can easily feel the difference. But the point is that completeness property states that whenever a set of real number is bounded, it attains its bound. That means whenever it is bounded, it has a least upper bound. And whenever it is bounded from below, it has a greatest lower bound. And one can easily apprehend that whenever it is bounded from upper side, what is bounded below, we have a particular value m or m plus 1 or m square or m cube, all are upper bound. So we are not interested about the larger upper bounds. We are interested about the least upper bound, the lowest value which becomes the upper bound of a set. And similarly, when it is bounded from below, we are interested about the greatest value, which is the lower bound. So any number which is more than this small m will not be a lower bound, and that is when we say that it has a GLB. And any number which is lower than this capital M will not be upper bound. So m minus epsilon, a value less than capital M, will not be a upper bound. Then only we say that capital M is a least upper bound, and any small increment of this capital M makes it, fails it to be a lower bound, and then only we say that small m is greatest lower bound. And whenever A is bounded, it attains its properties. And these concepts are very easily approached or apprehended with the help of the sequence of real numbers. How? Let us discuss a sequence one by n. So this, since n is a natural number, this has a limit point 0, and you can easily see that after a large value capital M, for all n which are large than capital M, you may choose this m to be 10 to the power 100, and another person may choose this capital M to be 10 to the power 1000, and another person may choose this capital M to be 10 to the power 1 lakh. Whatever you choose the value of capital M, you can easily see that the difference between 1 by n and 0 mod value, this is actually 1 by n. It becomes, since n is larger than this becomes 10 to the power minus 1000, and this can easily be chosen as a arbitrary small value. If you don't agree with this to be the arbitrary small value, you can choose this, but we can easily infer or conclude that this is a sequence of number which converges to 0.